Every image of a supernova cloud quietly tells the same comforting lie. It appears suspended in space, like colored smoke drifting through still air. Crimson filaments curl gracefully around glowing blue knots. Golden ribbons stretch across darkness with the elegance of ink dissolving into water. From Earth, through the patient eyes of space telescopes, these remnants of exploded stars resemble celestial paintings, beautiful enough to hang on the walls of museums, distant enough to admire without fear, but beauty, in astronomy, is often a trick created by distance. The cloud itself does not know it is beautiful. It is not floating peacefully. It is not resting after a great explosion. It is not even truly a cloud in the way the human mind instinctively imagines one. There is no soft mist waiting to part before an explorer. No quiet vapor illuminated by gentle starlight. No silent ocean of color. There is only matter rushing away from catastrophe. Even now, somewhere inside our galaxy, the remains of a star continue expanding into darkness. Every second, those fragments move farther apart. Every hour, shock waves sweep across regions larger than planetary systems. Every year, invisible particles race outward at speeds that would circle Earth many times before a human heartbeat could finish. And yet, from thousands of light years away, the violence has become so enormous that it looks still. Scale has hidden motion, distance has disguised catastrophe. Our eyes evolved beneath a warm atmosphere where storms pass overhead. Mountains remain where they have always been, and clouds drift slowly across familiar skies. We instinctively associate stillness with safety. If something appears calm, we assume its danger has ended. The universe rarely shares that assumption. A supernova cloud is what remains after one of nature's most energetic events. For a brief period, a single dying star can release more energy than our sun will emit during its entire lifetime of roughly 10 billion years. The explosion lasts only moments in cosmic terms. Its consequences continue for hundreds of thousands of years. The explosion ends. The cloud remembers. If it were somehow possible to stand inside an impossible thought, for reasons that will gradually become clear, you would not see colored gas surrounding you like morning fog. Human eyes would detect almost nothing at all. The particles are astonishingly far apart. The vacuum between them is so complete that inside loses much of its familiar meaning. You would be immersed in something that feels almost like nothing, and yet that nothing contains temperatures capable of stripping atoms apart. Magnetic fields stretching across incomprehensible distances, radiation invisible to every human sense, and fragments of heavy elements that once existed deep inside the heart of a star, older than our own civilization by millions of years. The greatest danger is not density, it is emptiness. This is one of the first places where ordinary intuition begins to fail. On Earth, we imagine danger as something crowded, fire pressing against skin, water surrounding the body, collapsing stone filling every direction. Survival often depends on escaping matter. In a supernova cloud, survival becomes impossible because there is almost no matter at all. The emptiness itself becomes the environment. That idea is difficult to hold in the mind. Our brains evolved to understand forests, deserts, oceans, and mountains. Even the emptiest desert still surrounds you with billions upon billions of air molecules in every breath. Every second of your life has unfolded within an atmosphere so dense that you have never truly experienced the vacuum that dominates almost the entire universe. We speak casually of outer space, but those words conceal a reality far stranger than language comfortably allows. The universe is not mostly stars. It is not mostly planets. It is not mostly galaxies. It is mostly absence. Stars are rare interruptions in an almost endless emptiness. Planets are rarer still. Entire civilizations occupy regions so small that the galaxy would never notice if they appeared or disappeared. A supernova cloud exists between these extremes. It is born from unimaginable violence, yet it expands into a universe that offers almost no resistance. Nothing meaningful slows it. Nothing gathers its scattered remains back together. The debris simply continues outward, year after year, century after century, millennium after millennium, long after every language spoken on Earth has changed beyond recognition. Long after every monument has weathered into dust. Long after our species itself has become memory or vanished entirely. The cloud will still be traveling, not because it has somewhere to go, but because the universe almost never asks anything to stop. Perhaps this is the most unsettling truth hidden inside those glowing photographs. They are not portraits of an event. They are portraits of momentum. We often think of explosions as brief moments of flash. A sound, a sudden ending. In the cosmos, an explosion can become a journey lasting longer than the rise and fall of entire civilizations. What appears frozen in a telescope image is actually caught during a process so vast that a human lifetime is too short to notice its movement. Reality has not paused. We simply arrive too briefly to watch it unfold, and that realization quietly changes something. The cloud is not waiting for us to understand it. It has already been traveling for centuries before the first telescope was built. It was already expanding before the first cities rose from river valleys. Some remnants visible tonight began their silent outward voyage while human beings were still learning to shape bronze. Long before anyone imagined that stars could die, the light reaching our eyes is not merely old. It is carrying evidence that the universe has been patiently continuing its work without us for an almost unimaginable length of time. The deeper we look into that drifting cloud, the less it resembles a beautiful object. It begins to resemble a message, one that says, without cruelty and without comfort, that the universe is far older, far quieter, and far less centered on observers than the human imagination has ever been prepared to accept. The night sky encourages a quiet misunderstanding. Stand beneath it on a clear evening, far from the glow of cities, and the universe seems comfortably organized. Bright stars appear scattered across a dark canvas. A faint band of the Milky Way stretches overhead like pale smoke. Here and there, a familiar constellation emerges from patterns our ancestors imagined thousands of years ago. Even without knowing their names, the stars seem permanent. They appear fixed in place, patiently watching generations come and go. It is an understandable illusion. Everything important in human history has unfolded beneath a sky that appears almost unchanged. Empires have risen. Religions have spread. Languages have been born and forgotten. Yet, Orion still returns each winter. The familiar curve of the Big Dipper still circles the northern horizon. The same stars that guided sailors across ancient oceans continue guiding satellites that orbit Earth today. Our brains naturally conclude that the heavens are stable. The universe allows us to believe this because our lives are extraordinarily short. A child looks upward and sees stars. An elderly person looks upward 80 years later and sees nearly the same stars. Between those two moments lies almost an entire human lifetime. Yet, for the galaxy, 80 years is not even the beginning of a heartbeat. During that time, light itself travels only 80 light years, a remarkable distance by earthly standards, but insignificant inside a galaxy nearly 100,000 light years across. Human experience measures time in decades. The universe measures it in transformations. This difference quietly shapes every instinct we possess. We think of mountains as permanent because they outlive us, even though they slowly rise and erode. We think of continents as immovable despite their relentless drift across Earth's surface. We imagine the sun as eternal because it has warmed every generation that has ever lived, despite the fact that it is already halfway through its own existence. Duration creates certainty. Longevity creates illusion. The same illusion follows us into astronomy. When we see an image of a nebula or a supernova remnant, we instinctively imagine something like weather. A cloud forms. It changes shape. It slowly disperses. The comparison feels reasonable because clouds are among the largest natural structures we encounter on Earth. But terrestrial clouds are tiny. Even the largest storm systems could disappear inside a minute fraction of a supernova remnant without leaving a noticeable trace. The comparison survives only because the human mind has no everyday experience with structures measured not in kilometers, but in light years. A light year is often introduced as a number about 9.46 trillion kilometers. The figure is accurate. It is also emotionally meaningless. A better way to understand it is through patience. The sunlight warming your face today left the sun about 8 minutes ago. The light reaching Earth from our nearest stellar neighbor beyond the sun began traveling more than 4 years before it arrived. When astronomers observe many famous supernova remnants, they are receiving light that departed before entire nations existed in their present form. The universe is not showing us what is happening. It is showing us what has already happened. Every glance into deep space is an encounter with history. That simple fact quietly overturns another comforting assumption. When we look at another person, we see them almost as they are. Light takes only fractions of a second to cross a room. Conversation feels immediate because reality arrives almost instantly. The cosmos does not grant that privilege. Every additional kilometer introduces delay. Every additional star increases the distance between event and observation. By the time light from a distant supernova reaches Earth, the expanding cloud may already have transformed into something entirely different. Astronomy is the study of messages that have spent centuries, millennia, or millions of years crossing silence. Imagine receiving a letter written before the first pyramids were built. Imagine answering it, knowing your reply would arrive millions of years after the sender had ceased to exist. That strange relationship between distance and time is the ordinary condition of the universe. The stars surrounding us are not neighbors in the familiar sense. They are separated by gulfs so immense that even light, the fastest thing known in nature, requires years simply to cross them. Between those stars lies a darkness so complete that individual atoms may drift for astonishing lengths of time without encountering another. Space is not crowded. It is overwhelmingly vacant. This emptiness explains something that photographs often conceal. The brilliant colors captured by modern telescopes do not represent scenes that a traveler would witness with naked eyes. Those colors are carefully collected over many hours, sometimes days, combining wavelengths beyond human vision into images that reveal structures too faint for ordinary sight. Without those techniques, many nebulae would appear as little more than ghostly smudges against blackness. The vivid crimson arcs and luminous blue filaments are real, but they are translations, scientific interpretations of light, so scarce that our eyes alone could never fully appreciate it. The universe is not withholding beauty. It is revealing how little of reality our senses evolved to perceive. That limitation extends beyond color. Human hearing detects vibrations traveling through air, in the vacuum between stars. There is almost no medium through which sound can move. An immense shock wave from a supernova can race across space, carrying enormous energy. Yet the event unfolds in profound silence. No thunder follows the explosion. No echo rolls through the galaxy. The violence exists without noise. This silence is difficult to imagine because every powerful event on Earth announces itself. Avalanches roar, volcanoes rumble, oceans crash against rock. We instinctively associate energy with sound because our planet wraps every experience inside an atmosphere. The galaxy does not. Its greatest events occur in quiet. This silence changes the emotional character of cosmic violence. A supernova is not a spectacular firework exploding beneath cheering skies. It is a star unmaking itself in an ocean of darkness where no ear can ever hear the event unfold. And yet, despite the silence, despite the emptiness, despite the unimaginable separation between one object and another, the universe remains connected, not by roads, not by rivers, not even by gravity alone. It is connected by light. Every photon leaving a distant cloud carries information across the abyss. Some travel for thousands of years before entering the mirror of a telescope. Others continue wandering indefinitely, never intercepted by a planet, a spacecraft, or an eye capable of recognizing their existence. Most light in the universe will never be seen. Most stories written into the cosmos will never be read. This is the comfortable picture beginning to fracture. The sky above us is not a collection of nearby lights decorating the darkness. It is an archive of ancient events arriving at different moments, separated by distances so vast that even the fastest messenger in existence struggles to bridge them. And somewhere within that archive drifts the expanding remains of a dead star still moving, still changing, still carrying the consequences of an explosion whose true nature only begins to emerge once our familiar picture of space has quietly fallen away. The death of a massive star is often described as an explosion. The word is correct. It is also profoundly inadequate. On Earth, an explosion is a brief interruption. A chemical reaction unfolds in fractions of a second. Energy rushes outward. The event ends almost as quickly as it begins, leaving behind smoke, fragments, and silence. A supernova follows a different rhythm. Its final explosion is merely the visible instant in a story that has been unfolding for millions of years, long before the brilliant flash reaches the surrounding galaxy. The star has already begun losing an invisible argument with itself. Every ordinary star exists because two enormous forces remain locked in perfect opposition. Gravity pulls relentlessly inward, attempting to compress the star into an ever smaller sphere. At the same time, nuclear fusion deep within the core pushes outward, releasing enough energy to resist that endless collapse. For most of a star's life, neither side wins. The balance appears effortless from a distance, but it is maintained by conditions so extreme that they have no equivalent on Earth. In the Sun's core, temperatures approach 15 million degrees Celsius. Hydrogen nuclei collide with such violence that they overcome their natural electrical repulsion, merging into helium and releasing energy according to one of the most famous relationships in physics. A tiny amount of mass becomes an astonishing amount of energy. That energy slowly climbs through the star. A single photon created in the Sun's core may require tens of thousands or even hundreds of thousands of years to reach the surface, continually absorbed and re-emitted as it struggles outward. Only then does it begin the familiar 8-minute journey toward Earth. Even sunlight has a history hidden beneath its apparent simplicity. For stars much larger than the Sun, this balance becomes more dramatic. Massive stars burn their fuel with extraordinary impatience. They are 20 times heavier than the Sun. The Sun does not live 20 times longer. It lives far less. Its enormous gravity demands greater pressure. Greater pressure demands higher temperatures. Higher temperatures accelerate fusion until the star consumes its nuclear fuel at a breathtaking rate. Imagine two candles. One burns gently through a quiet evening. The other has become a roaring torch, consuming itself so intensely that it illuminates an entire valley before vanishing long before dawn. Massive stars choose the second path. They live brilliantly. They die young for millions of years. The star quietly transforms itself from the inside out. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes neon. Neon becomes oxygen. Oxygen becomes silicon. Each new stage lasts less time than the one before it. Millions of years become hundreds of thousands. Hundreds of thousands become thousands. Thousands become years. Years become months. Months become days. Near the end, the pace becomes almost unimaginable. Silicon fusion, the final major stage before catastrophe, may last only about a day inside the largest stars. A lifetime of stability suddenly accelerates toward collapse. The star has entered a race it cannot win. Everything changes because of one element: iron. Among the countless atoms produced within stellar furnaces, iron occupies a peculiar position. Fusing lighter elements releases energy. Splitting extremely heavy elements can also release energy. Iron sits almost exactly between those two possibilities. It is the great energetic dead end. When the key fills with iron, fusion can no longer support the weight pressing down from above. The engine that held gravity at bay for millions of years quietly falls silent. Nothing dramatic is visible from outside. The star still shines. Its surface continues, radiating into space, across the galaxy. No civilization watching from a distant planet would notice anything unusual. But beneath that familiar light, gravity has finally been left alone. And gravity is patient. It does not become stronger. It simply stops being opposed. The collapse begins with astonishing speed. The iron core, larger than Earth, yet containing well over a solar mass of material, begins falling inward. Matter that once required millions of years to assemble compresses in less than a second. To appreciate this transformation, numbers alone are insufficient. Imagine every city, every ocean, Every mountain, every living creature on Earth, compress the entire planet until it fits inside a sphere only a few kilometers across. Now imagine something even more extreme occurring to a mass greater than the Sun. The density becomes so enormous that atoms themselves cannot survive unchanged. Electrons are forced into protons. The distinction between familiar matter begins dissolving. Neutrons dominate. The core stiffens with extraordinary suddenness. The collapse, falling at a significant fraction of the speed of light, slams into this newly incompressible neutron-rich core and rebounds outward. What follows is not merely an explosion. It is a shockwave born from the collapse of reality at the atomic scale. For decades, astronomers struggled to understand why this shockwave succeeds. Early computer models often predicted failure. The outward-moving shock stalled before escaping the star. The solution proved even stranger. Neutrinos. These ghostly particles are among the least interactive objects in the universe. Trillions pass through your body every second without leaving any trace. A sheet of lead 1 light-year thick would still fail to stop all of them. Yet during our collapse, the forming neutron star produces such an overwhelming flood of neutrinos that they briefly become one of the dominant forces shaping the explosion. Roughly 99% of the energy released by a core collapse supernova escapes as neutrinos. Not light, not heat, not the brilliant colors captured by telescopes. Invisible particles carry almost everything away. The visible explosion, the spectacle admired across galaxies, is merely a tiny fraction of the total event. Again, intuition quietly fails. We assume the brightest thing must also be the most energetic. The universe disagrees. When the shock wave finally breaks through the star's outer layers, material that had been forged over millions of years is hurled into interstellar space. Carbon, oxygen, silicon, calcium, nickel, iron, and dozens of heavier elements created during the violence itself. Some exist for only moments before decaying into more stable forms. Others will survive for billions of years. Among them are atoms that may one day become part of entirely different worlds. The calcium in the bones of an animal, the iron carried by blood, the gold inside a wedding ring, the uranium locked within ancient rock. These elements are not ordinary debris. They are the interior of a star. Suddenly exposed to the galaxy for the first time, the explosion tears open what gravity had hidden for millions of years. From a great distance, observers see only a point of light growing impossibly bright. For weeks, a single supernova may outshine an entire galaxy of billions of stars. Then the brilliance fades, the headlines end, the photographs become familiar. The event appears finished, but the explosion was never the destination. It was only the release. The true story begins afterwards, when the expanding material enters a universe almost completely empty, carrying with it impossible temperatures, tangled magnetic fields, unstable radioactive isotopes, and the chemical seeds from which future planets and perhaps future observers will eventually emerge. The star is gone. Its influence has only begun. What remains is neither simply ash nor simply gas. It is the beginning of an environment unlike any other in the known universe, one whose immense scale and hidden complexity make the original explosion seem almost like a prologue. For most of human history, the word inside has carried a reassuring meaning. Inside a forest, there are trees. Inside an ocean, there is water. Inside a mountain, there is rock. Inside a cloud, there is moisture suspended in air. Every environment we have ever evolved to understand surrounds us with matter. Our senses are designed to interpret surfaces, textures, temperatures, sounds, and movement through substances that remain comfortably familiar. But a supernova cloud quietly dismantles that entire idea. It asks a question that feels almost impossible to answer. What does it mean to be inside something that is almost entirely empty? The answer is stranger than almost any work of science fiction has dared to imagine, because reality has no obligation to resemble our intuition. Suppose, for a moment, that every impossible engineering problem had somehow been solved. Imagine a capable of surviving temperatures beyond imagination, shielding its occupants from lethal radiation, resisting impacts from particles traveling at thousands of kilometers per second, and functioning without any nearby star to provide warmth or orientation. Now imagine that vessel entering a famous supernova remnant from Earth. Telescopes have taught us to expect magnificent curtains of glowing color, crimson arcs, sapphire wisps, golden knots suspended against blackness. We have seen them so many times that the images have become almost familiar, but familiarity has been manufactured by distance. As the spacecraft crossed the boundary of the cloud, almost nothing dramatic would happen. There would be no visible wall, no sudden mist, no curtain of luminous gas, no moment when darkness gave way to color. Because there is no edge in the way the human mind expects an edge to exist. The cloud has boundaries only in the statistical sense. Its particles gradually become less numerous until, eventually, astronomers decide that the surrounding interstellar medium has become more dominant than the expanding debris itself. Nature never draws the line, humans do. The first sensation would not be one of entering a place. It would be the unsettling realization that there is almost nothing to enter, even in the densest filaments of many supernova remnants. The matter is astonishingly sparse. On Earth, a single cubic centimeter of air contains roughly 25 quintillion molecules. Every breath is an encounter with unimaginable abundance. Inside much of a supernova cloud, that same volume might contain only a handful of atoms, sometimes fewer, sometimes none at all. The difference is so extreme that language begins to lose its usefulness. We casually describe these remnants as clouds because we have no better word. In truth, they are closer to enormous patterns drawn across emptiness. Imagine dissolving Earth's entire atmosphere until it expanded across distances measured in light years. Imagine every molecule becoming so isolated that individual atoms drift for years before approaching another. Now remove nearly all sound. Remove every familiar smell. Remove gravity strong enough to suggest direction. Remove the horizon. Remove weather. Remove any reliable distinction between above and below. You have not yet recreated a supernova cloud. You have only begun removing the assumptions that Earth quietly provides every moment of your life. The greatest challenge would not be survival, it would be orientation. Human beings evolved in environments where every direction contains information. The ground tells us where to stand. The sky tells us where to look. Mountains, rivers, coastlines, trees, buildings, and stars create a continuous framework from which our brains construct reality. Inside an expanding supernova remnant, that framework disappears. There is no landscape. There is only volume. The nearest visible structure might be billions of kilometers away. It could appear no larger than a faint thread crossing darkness. Despite containing enough material to build countless planetary systems, distance ceases to behave emotionally. On Earth, something that looks close usually is close. In a supernova cloud, appearances become deceptive. A glowing filament stretching across your field of view may actually be hundreds of billions of kilometers distant, while another invisible stream of particles races directly through your location without offering any visual clue at all. Space becomes profoundly dishonest. And then there is the temperature. When people imagine cold space, they often picture freezing darkness. That expectation comes from everyday experience. On Earth, temperature is something carried by air. Cold surrounds us because molecules repeatedly collide with our skin, carrying less energy than our bodies possess. In deep space, almost no molecules exist to perform that exchange. The vacuum itself is not cold in the ordinary sense. Yet within a young supernova remnant, individual particles can possess temperatures reaching millions of degrees. This sounds impossible. How can something so hot exist inside something so empty? The answer lies in another misconception inherited from everyday life. We think of temperature as something we feel. Physics defines it differently. Temperature measures the average energy of particles, not the amount of matter present. A single grain of sand, heated until it glows white, contains extraordinary energy. A furnace filled with glowing metal contains vastly more because there is vastly more material. Inside a supernova cloud, particles move with astonishing energy, but there are so few of them that they cannot efficiently transfer heat to a passing object in the familiar terrestrial way. The environment becomes simultaneously unimaginably hot and eerily incapable of warming you in any ordinary sense. The contradiction feels uncomfortable because it violates instincts refined over hundreds of millions of years. Reality is not obligated to preserve those instincts beyond Earth. The cloud hides another invisible architecture: magnetic fields. On Earth, magnetism is associated with compasses or refrigerator doors, subtle effects barely noticed during daily life. Inside a supernova remnant, magnetic fields become enormous sculptors. They bend streams of charged particles into graceful arcs extending across light years. They compress plasma into delicate filaments that appear almost woven by invisible hands. They accelerate electrons until they emit radiation spanning radio waves, visible light, X-rays, and beyond. The glowing structures captured by telescopes are not merely drifting smoke. They are matter being organized by forces no human eye can perceive directly. The cloud begins to resemble less a weather system than an immense machine, not a machine with purpose, a machine with consequences. Every expanding shell carries turbulence. Every shock front reshapes surrounding gas. Every collision between fast-moving debris and the interstellar medium generates new complexity. The remnant refuses to settle into simplicity because the universe itself rarely chooses the simplest path. Chaos becomes structure. Structure becomes turbulence. Turbulence becomes new patterns, all unfolding over centuries and millennia. So gradually that the entire process appears motionless to observers whose lives last less than a century. This is where the familiar mental picture finally breaks. A supernova cloud is not a colorful object suspended in space. It is a continuously evolving physical environment whose true character is almost entirely invisible to unaided human senses. The colors are translations. The brightness is selective. The apparent stillness is an illusion born from enormous scale. Even the word cloud has become a quiet compromise between reality and imagination, because what actually exists is stranger, an expanding architecture of plasma, radiation, magnetic fields, shock waves, unstable atoms, an almost unimaginable emptiness, occupying a volume so vast that the human mind instinctively mistakes it for nothing at all. And yet, despite that overwhelming emptiness, this fragile-looking structure possesses enough influence to reshape entire regions of the galaxy. The question is no longer what exists inside the cloud. The more unsettling question is how something so empty can become one of the most powerful architects of everything that comes after. It is only after abandoning the familiar idea of a cloud that another misconception quietly appears. We continue to imagine it as a destination, a place, a region of space with an inside and an outside. But a supernova remnant is not truly a location. It is a process that has become so enormous we mistake it for geography. Imagine watching a ripple spread across the surface of a pond. For a few seconds, your eyes easily follow its expanding circle. Now imagine the ripple continuing not for seconds, but for 50,000 years. Imagine it crossing an ocean instead of a pond. Eventually, the ripple would become so vast that no single observer could recognize it as movement anymore. It would simply seem to exist. That is what has happened inside many supernova remnants. Expansion has become architecture. Motion has become landscape. The famous remnants photographed by modern observatories are often dozens of light years across. The Veil Nebula, the remains of a star that died perhaps 10,000 years ago, stretches across a region of space so immense that if it replaced our solar system, every planet, including distant Neptune, would disappear into a tiny point lost deep inside its interior. The Crab Nebula, born from the supernova witnessed by astronomers in the year 1054, continues expanding every single day. No human observer notices the movement directly, not because it has stopped, because our lives are too brief. Even during the centuries since Chinese astronomers carefully recorded the appearance of the guest star, the nebula has continued quietly enlarging while kingdoms disappeared. Continents were explored, industries rose, and spacecraft left Earth for the first time. Human history has unfolded inside the lifetime of an expanding cloud. That comparison begins to reveal a deeper truth. We instinctively divide reality into events and objects. Lightning is an event. A mountain is an object. A hurricane is an event. An island is an object. Supernova remnants refuse this distinction. They remain events that eventually become landscapes. The explosion never truly ends. Its consequences simply become too large for human intuition to recognize as consequences. This is where scale becomes psychologically dangerous. Our minds evolved to estimate distances measured in footsteps. A long journey might require days. An ocean crossing once demanded months. Even the first voyages to the moon occupied only a few days of human experience. Nothing in our evolutionary history prepared us to emotionally understand light years. Suppose you could travel at the speed of the fastest spacecraft ever launched from Earth. NASA's Parker Solar Probe, at its maximum speed near the Sun, exceeds 600,000 kilometers per hour. It is one of humanity's greatest engineering achievements at that astonishing velocity. Reaching the nearest star would still require thousands of years. Crossing a large supernova remnant would consume generations beyond counting. The crew would not merely grow old. Entire civilizations would need to replace one another while the journey continued. Languages would evolve, religions would emerge and disappear. Maps of Earth would be redrawn countless times, and still the opposite side of the cloud might remain unimaginably distant. Distance ceases to belong to transportation. It becomes history. Now imagine reducing your speed to something more familiar. An airliner, a racing car, a person walking. The numbers become almost absurd. Walking continuously without rest. Crossing even a modest supernova remnant would require far longer than Homo sapiens has existed as a species. The comparison is intentionally impossible, not to dramatize the scale, but because ordinary comparisons have already failed. Our brains quietly compress astronomical distances until they feel emotionally manageable. Reality refuses that compression. Inside these remnants, individual filaments of glowing plasma can themselves stretch across distances larger than the separation between our sun and many nearby stars. What appears in a photograph as a delicate thread is often an immense river of ionized gas sculpted by magnetic fields over thousands of years from Earth. A filament occupies a few millimeters on a computer screen. In reality, it may contain enough material to build countless future planetary systems. Perspective quietly betrays us. The same deception occurs with density. Because the cloud is so enormous, even tiny concentrations of matter become cosmically significant. Imagine placing a single grain of sand inside a cathedral. Now enlarge the cathedral until it becomes the size of a continent. The grain becomes almost impossible to find. Yet if billions upon billions of grains were distributed with similar sparseness across that immense volume, they would still represent an extraordinary amount of material. This is how supernova remnants behave. Their particles are astonishingly dispersed. Their total mass remains immense. A typical core collapse supernova may eject several times the mass of our sun. That material does not disappear. It simply occupies a region so vast that emptiness dominates every local experience. This tension between abundance and absence defines much of astrophysics. The universe rarely gathers matter together, it spreads it apart. Gravity spends billions of years patiently collecting material into stars. A single supernova redistributes much of that achievement in moments. Construction may require millions of years. Dispersal takes seconds. And yet the dispersal is not destruction in the ordinary sense. It is redistribution. Every expanding shell carries carbon that may someday become forests, silicon that may crystallize into mountains, iron that may flow through the blood of creatures not yet imagined, oxygen that may eventually fill the atmospheres of unborn worlds. Nothing has meaning yet. Everything possesses potential. The cloud becomes a vast inventory traveling through darkness. But inventories also change. As the expanding shock wave moves outward, it eventually encounters the interstellar medium, the extraordinarily thin gas already drifting between stars. Compared with Earth, this surrounding medium is almost inconceivably empty. Compared with the interior of the expanding remnant, it is enough to matter. The collision is gentle by terrestrial standards, violent by cosmic ones. The leading edge compresses surrounding gas. Magnetic fields intensify. Electrons accelerate toward nearly the speed of light. X-rays emerge. Radio waves spread across the galaxy. Invisible energy fills regions where ordinary eyes would perceive only darkness. The cloud is not merely expanding, it is interacting, like a ship crossing an ocean. It leaves a wake, except this wake may influence regions of space spanning dozens or even hundreds of light years. Every year, the boundary advances. Every century, the surrounding galaxy changes almost imperceptibly. Every millennium, new structures emerge. Nothing happens quickly enough for a single observer to witness. Everything happens continuously. This mismatch between cosmic time and biological time quietly isolates humanity from much of reality. We live too briefly to watch galaxies rotate, too briefly to see stars born, too briefly to notice supernova remnants truly expanding. Astronomy, therefore, becomes an unusual science. Rather than observing one event unfold, astronomers compare countless objects frozen at different moments of similar histories. A young remnant, an older remnant, a fading remnant. By assembling these separate snapshots, they reconstruct processes lasting far longer than any civilization has endured. In a sense, humanity has learned to study time without living through it. That achievement is remarkable. It is also humbling, because every image we analyze captures only an instant in a journey vastly exceeding our own. The cloud continues moving after the telescope closes, after the observatory sleeps, after the scientists retire, after every observer who first studied it has become part of history themselves. The remnant remains indifferent to witnesses. It expands because momentum persists. It evolves because physics continues. It does not require memory, only time. And time is the one resource the universe possesses in almost unlimited abundance. Viewed this way, the cloud ceases to resemble debris from a dead star. It becomes something much larger, a slow-moving continent of transformation crossing the galaxy, carrying within its immense emptiness the raw ingredients from which entirely new astronomical histories will eventually begin. The explosion no longer appears to be the central event. The expansion is, and the expansion has scarcely begun. The expanding cloud appears graceful only because almost everything shaping it is invisible. If human vision extended beyond the narrow band of light between red and violet, the familiar photographs of supernova remnants would become almost unrecognizable. The elegant filaments would dissolve into an intricate architecture of X-rays, radio waves, gamma rays, ultraviolet light, and magnetic structures stretching across distances that no ordinary landscape could ever imitate. Reality has never been confined to what the eye can see. It is simply that the eye evolved for forests instead of galaxies. The world around us is rich in visible light because our nearest star emits most of its energy there, and because Earth's atmosphere happens to be transparent to those wavelengths. Evolution took advantage of that fortunate coincidence. The universe never made the same decision. Much of what truly matters inside a supernova remnant lies beyond human senses entirely. Imagine standing inside an ancient cathedral at night. The stone walls disappear into darkness. The ceiling becomes invisible. You know the building surrounds you, yet your eyes reveal only fragments illuminated by a single candle. Now imagine replacing that candle with hundreds of different lamps, each revealing an entirely different architecture. Hidden inside the same structure, one exposes the wooden beams, another reveals moisture within the stone, another highlights tiny fractures running through the walls, another uncovers invisible currents of warm air slowly circulating beneath the roof. None of the lamps are lying. Each is simply translating a different aspect of reality. Modern astronomy works in much the same way. Radio telescopes reveal enormous clouds of cold hydrogen and the synchrotron radiation produced by relativistic electrons spiraling through magnetic fields. Infrared observatories detect dust warmed by nearby stars. Optical telescopes capture glowing atoms excited by shock waves. Ultraviolet instruments expose energetic transitions hidden from ordinary sight. X-ray observatories uncover plasma heated to millions of degrees. Gamma-ray detectors trace the signatures of radioactive decay and particles accelerated to astonishing energies. Together, these observations reveal something profoundly different from the colorful clouds familiar in public imagination. They reveal machinery, not machinery designed with intention, machinery emerging naturally from physical law. One of the most important components of this machinery is plasma. The word rarely appears in everyday conversation, Yet, plasma is the most common state of ordinary matter in the visible universe. Solid rock, liquid water, atmospheric gas. These dominate human experience. Stars do not share that preference. Neither do supernova remnants. Plasma forms when atoms possess so much energy that electrons no longer remain comfortably attached to their nuclei. Instead of neutral atoms drifting quietly through space, there exists an electrically charged mixture of ions and free electrons responding continuously to magnetic and electric fields. It behaves unlike any familiar substance. Smoke drifts because of wind. Water flows because of gravity. Plasma dances according to electromagnetism. This distinction changes everything. Inside a supernova remnant, magnetic fields become invisible rivers directing the motion of charged particles. Electrons spiral around field lines instead of traveling straight. Vast loops form. Thin filaments emerge. Regions compress while others stretch apart from millions of kilometers away. These structures appear almost artistic from within. They would represent an environment in constant negotiation between energy and order. The remarkable aspect is that these magnetic fields are extraordinarily weak by everyday standards. A small refrigerator magnet produces a stronger magnetic field than many regions of interstellar space. Yet size transforms weakness into influence across light years of distance. Even delicate magnetic fields gradually shape enormous quantities of plasma. Again, intuition quietly fails on Earth. Stronger usually means more important. The galaxy rewards persistence instead. A faint influence acting continuously for thousands of years can accomplish what overwhelming force cannot achieve in moments. Shock waves provide another example. When we hear the phrase on Earth, we imagine the deafening pressure front from an explosion or the sonic boom of an aircraft exceeding the speed of sound. Inside a supernova remnant, the concept survives. The experience does not. There is almost no atmosphere through which sound can travel. Yet, disturbances still race outward because the expanding debris collides with surrounding plasma. The shock compresses gas. It strengthens magnetic fields. It heats matter to extraordinary temperatures. It accelerates particles to velocities approaching the speed of light. These are called collisionless shocks because individual particles often do not strike one another directly. Instead, collective electromagnetic interactions transmit energy across enormous distances. The name itself hints at how foreign this environment has become. On Earth, collisions explain almost everything. In much of interstellar space, fields replace contact. Invisible forces organize matter that rarely touches. Among the greatest consequences of these shocks is the production of cosmic rays. Despite the name, they are not rays at all. Most are individual atomic nuclei protons, helium nuclei, and heavier elements accelerated until they carry energies almost beyond imagination. For over a century, scientists have investigated their origins, although multiple sources contribute. Supernova remnants are now understood to be among the galaxy's most powerful natural particle accelerators. No civilization built them, no engineer designed them, yet they routinely propel subatomic particles to energies vastly exceeding those produced in humanity's largest machines. The Large Hadron Collider, beneath the French-Swiss border, represents one of the most sophisticated scientific instruments ever constructed. Its circular tunnel stretches 27 kilometers. It required decades of planning, international cooperation, and extraordinary precision. A supernova remnant casually performs related feats across regions measured in light years. Nature does not imitate technology. Technology slowly learns to imitate nature. Then there is radioactivity. The explosion itself manufactures unstable isotopes that continue changing long after the initial flash has faded. Nickel-56 decays into cobalt-56. Cobalt-56 decays into iron-56. Each transformation releases energy. Each decay contributes to the changing brightness astronomers observe as the remnant evolves. In a sense, the cloud carries countless tiny clocks, not clocks measuring hours, clocks measuring transformation. Every radioactive isotope quietly announces how much time has passed since the star died. The remnant becomes both archive and chronometer. Some radioactive nuclei disappear within days. Others persist for centuries. Still others survive for hundreds of thousands of years, allowing astronomers to reconstruct explosions long after visible evidence has faded. Matter remembers, not consciously, physically. Its composition preserves events more faithfully than memory ever could. This growing complexity reveals why the word aftermath feels increasingly inadequate. An aftermath suggests a period following the main event. The supernova remnant refuses such simplicity. The explosion initiates processes that continue interacting, evolving, and generating new phenomena over immense spans of time. Every expanding shell modifies its surroundings. Every magnetic filament redirects charged particles. Every radioactive atom contributes energy. Every shock front reshapes the medium into which it travels. Nothing remains static. Nothing truly finishes. The cloud resembles an ecosystem governed not by biology, but by physics. Energy flows. Structures emerge. Structures dissolve. New structures replace them. No organ directs the process. No central intelligence coordinates the whole. Order appears because the laws of nature permit it to appear. Perhaps this is the deepest scientific lesson hidden within the remnant. The universe rarely requires complexity to be designed. Given sufficient time, sufficient energy, and sufficient space, complexity often assembles itself, not perfectly, not permanently, but persistently, inside the expanding remains of a dead star. Invisible machinery continues its patient work while millions of years pass unnoticed. The brilliant explosion that first announced the star's death has become only a distant memory. The quieter processes have taken over. They are slower, they are subtler, and in many ways, they are far more consequential than the explosion that created them, because they do not merely preserve the past. They quietly prepare the conditions from which an entirely different future will eventually emerge. There is a comforting habit woven into the way human beings tell stories. We separate destruction from creation. A forest burns. Later, new trees grow. A city falls. Eventually, another city rises. A species disappears. Another slowly evolves to occupy the empty space. One event belongs to the past. The other belongs to the future. Between them lies a pause, a moment when destruction has ended before creation begins. The universe rarely grants such pauses. Inside a supernova remnant, destruction and creation occur simultaneously. The cloud itself exists because something immense has died. Yet every kilometer through which it expands quietly prepares conditions that could eventually allow entirely new stars, new planets, and perhaps new forms of life to emerge. The same event performs both roles at once. This is where the emotional meaning of a supernova begins to change. Until now, it has been tempting to think of the explosion as an ending. A star exhausts its fuel, gravity wins, the core collapses, the outer layers are thrown into space, the star is gone. The story appears complete. But physics does not recognize endings in quite the same way human beings do. It recognizes transformation. The carbon drifting through the cloud no longer belongs to the star that created it. The oxygen no longer exists to support fusion inside a stellar core. The iron has been released from unimaginable pressure. Every atom has entered a different chapter of its existence. Nothing has vanished. Its relationships have merely changed. This distinction seems subtle. It is not. Everything familiar on Earth depends upon it. Every breath you have ever taken contains oxygen that was forged inside stars that died billions of years before our sun existed. The calcium strengthening your bones was assembled under temperatures no planet could survive. The phosphorus helping every cell in your body store energy originated inside stellar furnaces that disappeared long before Earth became a world. Even the iron quietly carried through your bloodstream has experienced a history almost impossible to imagine. Before it became part of your body, it belonged to a star, not metaphorically, literally. It once existed inside an object so massive that gravity compressed matter beyond ordinary comprehension. It endured temperatures of millions of degrees. It survived the collapse of an entire stellar core. It escaped within an expanding cloud that traveled through interstellar darkness for immense stretches of time, only after countless additional events. New clouds, new stars, new planets, geological change, biological evolution. Did that same atom become part of a living organism capable of wondering where it came from? The atom traveled farther than any human ever will. It simply did so without intention. This realization quietly dissolves another familiar boundary. We often imagine ourselves standing apart from the universe, observers looking outward, scientists studying distant objects, civilizations mapping the stars. But the distinction is incomplete. The observer is built from the observed. There is no clean separation. Every telescope constructed by human hands is itself assembled from atoms born in extinct stars. Every astronomer analyzing supernova remnants possesses a brain whose chemistry depends upon elements released by explosions similar to those being studied. The universe has become aware of part of its own history through materials that originated within that history, not because consciousness was inevitable, because physics permitted the possibility. And yet this comforting connection carries an unsettling implication. If our existence depends upon stellar death, then life is not the opposite of catastrophe. Life is one of catastrophe's distant consequences. Without supernovae, the early universe would have remained chemically simple: hydrogen, helium, tiny traces of lithium, enough to produce stars, not enough to produce rocky planets, not enough to build oceans, not enough to construct the astonishing complexity required for biology. The first generations of stars lived inside a universe almost unimaginably barren compared with the one surrounding us today. Their planets, if any existed at all, would have been profoundly different. The chemistry of possibility had not yet been written. Only after enormous stars began dying did the periodic table gradually spread across galaxies. Every explosion enriched the surrounding medium. Every remnant carried new ingredients outward. Every generation of stars inherited slightly more complexity than the generation before. The Milky Way slowly became chemically richer, not because anyone intended improvement, because stars continued living and dying. The process resembles an inheritance. Each stellar generation leaves something behind. The next receives it, then passes even more to those that follow. Our own solar system, formed approximately 4.6 billion years ago, from a molecular cloud already enriched by many previous stellar deaths. Evidence remains embedded within ancient meteorites, Tiny grains preserve isotopic signatures, pointing toward radioactive elements created shortly before the sun itself formed. Some astronomers suspect that a nearby supernova may even have helped trigger the collapse of the cloud from which our solar system emerged. If so, the explosion of one star may have directly contributed to the birth of another, not through intention, through pressure. A shockwave moving across interstellar space compresses nearby clouds. Gravity, previously balanced against internal pressure, gains a slight advantage. The cloud begins collapsing. Regions become denser. Protostars appear. Nuclear fusion ignites. A new generation of sunlight begins. Violence quietly becomes fertility. Again, intuition resists. On Earth, explosions scatter. In galaxies, explosions can also gather by compressing distant clouds. The outward moving shockwave encourages matter to assemble. The same force that tears one star apart may ultimately help dozens of others come into existence. Creation does not follow destruction. Creation emerges from it. This cycle unfolds across extraordinary spans of time. A supernova remnant may remain visible for tens of thousands of years. The enriched material continues mixing with surrounding gas for millions. New molecular clouds evolve. New stars ignite. New planetary systems slowly assemble from disks of dust and gas. Rocky worlds cool. Atmospheres form. Water accumulates. Chemistry experiments patiently for hundreds of millions of years. Only then might biology begin. The consequences of one stellar death echo forward through intervals so immense that ordinary chronology becomes almost meaningless. No civilization could witness the entire sequence. No species experiences it from beginning to end. The universe works on timescales too generous for memory. Imagine planting a single seed, knowing the tree would not appear for 50 million years. Not because growth is slow, because every stage requires another process before it. That is how galaxies build complexity. One event prepares another. That event prepares another. Nothing arrives independently. Everything inherits. Yet inheritance also means uncertainty. Most of the material expelled by a supernova will never become part of a living world. Much of it will drift through interstellar darkness until another event scatters it again. Some atoms may orbit the galaxy for billions of years without ever joining a planet. Others may be swallowed by black holes. Some may become trapped within frozen bodies, wandering endlessly between stars. The universe wastes almost everything, not through carelessness, through abundance. For every world capable of sustaining oceans, immeasurably more matter remains forever silent. For every observer who eventually asks where the atoms came from, countless atoms never participate in anything more complicated than drifting through emptiness. The cloud therefore represents both astonishing possibility and overwhelming indifference. It distributes the ingredients of future life everywhere. It guarantees nothing. No destination has been chosen. No outcome has been promised. The expanding remnant simply releases opportunity into a universe where gravity, chance, chemistry, and time negotiate what follows. This is perhaps the quietest form of violence, not violence that seeks to destroy, violence that makes creation possible without caring whether creation ever occurs. The explosion does not celebrate new worlds. It does not mourn the old star. It simply obeys the same physical laws that govern the universe long before planets existed and will continue governing it long after every civilization has faded. From our perspective, this feels emotionally difficult. We instinctively search for purpose. The remnant offers only process. And perhaps that is more unsettling because somewhere inside the expanding cloud, drifting through a darkness almost impossible to imagine, are atoms that may one day become part of another sky, another ocean, another living mind. Most will never reach such a destination. A few almost certainly will. The cloud does not know the difference. It continues expanding all the same. There comes a point where even the idea of an expanding cloud is no longer large enough. Until now, it has been possible to imagine a supernova remnant as an isolated phenomenon, a spectacular event unfolding within an otherwise quiet galaxy. A star dies, its debris expands, the surrounding space responds. The physics becomes increasingly intricate, but the story still seems self-contained. This is where the picture begins to break down, because a supernova cloud is almost never alone. The Milky Way contains hundreds of billions of stars. Most live quietly for billions of years, shining with remarkable stability. But scattered among them are the rare giant stars, so massive that their lives burn with extraordinary urgency. They exhaust themselves quickly. They die young. And when they die, they do not simply disappear. They seed the galaxy. One explosion becomes another source of heavy elements, another expanding shell, another shockwave moving through interstellar darkness, another contribution to an immense circulation of matter that has been continuing for almost the entire history of the galaxy. The remnant you have been imagining is not unique. It is one voice inside a chorus, too vast to hear all at once. Across the Milky Way, stars are continually being born while others quietly approach collapse. Somewhere, at this very moment, an elderly red giant is shedding its outer atmosphere. Elsewhere, a massive blue star is exhausting the final stages of nuclear fusion. In another region, a molecular cloud is slowly collapsing under its own gravity, gathering enough density for new sunlight to ignite. The galaxy is never still. It merely changes too slowly for us to notice. Human history encourages us to think in straight lines. Birth, growth, age, death. The universe prefers circles, not perfect circles. Cycles. Matter moves from one form to another, then another again, over intervals so immense that beginnings and endings become difficult to distinguish. The hydrogen born during the first minutes after the Big Bang became stars. Those stars manufactured heavier elements. Supernovae scattered them. The scattered material assembled into new stars. Around some of those stars, planets formed. On at least one such planet, chemistry crossed a threshold into biology. Eventually, consciousness emerged. That consciousness built telescopes. Those telescopes looked back toward the supernova remnants, from which the atoms of their mirrors had ultimately originated. The cycle briefly became aware of itself, not permanently, only for a moment. That moment is us. It is tempting to imagine this awareness as something exceptional. Perhaps it is. Perhaps it is unimaginably common. The universe has not yet revealed the answer, but whichever possibility is true, the cycle continues without interruption. Stars are not manufactured in isolation. Most emerge within giant molecular clouds, vast regions containing cold hydrogen, helium, dust, and traces of heavier elements inherited from previous generations of stellar death. These clouds are among the coldest places in the galaxy. Temperatures fall to only a few degrees above absolute zero. Atoms drift slowly. Radiation weakens. Darkness deepens. Nothing about them appears dramatic. Yet hidden inside this extraordinary stillness lies enormous potential. Gravity waits. For millions of years, these clouds may remain almost unchanged. To human eyes, they would seem eternal, but equilibrium is fragile. A passing spiral arm of the galaxy may compress the cloud. Nearby stellar winds may disturb it. Another supernova shockwave may arrive after traveling through interstellar space for tens of thousands of years. The cloud barely notices the impact. Its response unfolds over millions of years. A slight increase in density allows gravity to strengthen. Matter begins gathering. The densest regions collapse more quickly. Filaments form within those filaments. Knots appear inside those knots. Protostars emerge. Each newborn star is not simply the child of one cloud. It is the descendant of countless extinct stars whose material has been mixed together across cosmic time. No atom remembers where it originated. The galaxy remembers through composition. This changes the meaning of ancestry. Human families trace their history through generations, measured in decades. Civilizations trace theirs through centuries. The atoms inside a forming star trace theirs through billions of years and innumerable stellar deaths. Its family tree spans much of galactic history. Our own sun belongs to this inheritance. When it ignited approximately 4.6 billion years ago, it was already composed of recycled material. The Earth condensed from the remaining disk surrounding that young star. Every mountain, every ocean, every continent, every living organism, every future human being, all emerged from matter that had already lived previous astronomical lives. The solar system is not an original creation, it is a reconstruction. This idea becomes even more unsettling when we widen the scale again. The Milky Way itself is not isolated. It drifts among dozens of smaller satellite galaxies, while moving through the local group, a collection of more than 50 galaxies bound together by gravity. Beyond the local group lies the Virgo supercluster. Beyond that, even larger structures extend across hundreds of millions of light years, forming immense filaments surrounding equally immense voids. Galaxies themselves become particles. Clusters become droplets. Superclusters resemble strands woven through an almost unimaginable darkness. The universe repeats familiar patterns across astonishing scales. Clouds become stars. Stars become galaxies. Galaxies become clusters. Clusters become cosmic webs. At every level, emptiness dominates. Matter merely sketches delicate structures across an overwhelming background of absence. The supernova cloud that once seemed unimaginably vast now occupies a position almost too small to notice. A structure spanning dozens of light years becomes insignificant inside a galaxy 100,000 light years across. That galaxy becomes modest within a group millions of light years wide. The group itself nearly disappears inside structures extending across hundreds of millions of light years. Perspective does not merely expand, it erases certainty. Each time the scale increases, previous definitions of large quietly collapse. This is where existential discomfort begins to deepen. Human beings naturally search for permanence. We build monuments from stone because stone appears durable. We preserve books because written words seem capable of surviving generations. We send spacecraft into orbit, believing the heavens represent stability. But every level of cosmic organization is temporary. Stars evolve, nebulae disperse, galaxies collide, clusters merge. Even the cosmic web itself continues changing as gravity slowly reshapes the universe over incomprehensible spans of time. Nothing has reached its final form. Everything is passing through one. The supernova cloud therefore occupies a strangely humble position. It is not merely the remains of one star. It is one brief stage inside a chain of transformations, stretching from the earliest moments after the Big Bang, toward futures no observer can fully imagine. Its existence feels immense to us because our perspective is so small. To the galaxy, it is routine. To the universe, it is almost ordinary. Yet ordinary does not mean unimportant. Without these remnants, galaxies would remain chemically impoverished. Without recycled heavy elements, rocky planets would scarcely exist. Without generations of stellar death, the conditions required for biology might never arise. The universe builds complexity by refusing to preserve simplicity. Every act of construction demands previous acts of dissolution. Every stable world inherits ancient catastrophes. Every quiet night beneath familiar stars conceals histories of unimaginable violence. The comfort of the sky has always depended upon events too slow, too distant, and too vast for ordinary perception. Perhaps this is why the universe feels increasingly lonely, the more honestly it is understood. Not because life is impossible, not because beauty is absent, but because everything beautiful exists inside processes so immense that no single observer can ever witness the whole. A civilization may study one supernova remnant, another civilization, elsewhere and elsewhen, may observe the birth of a molecular cloud enriched by that same remnant. Neither will know the other. Neither will see the complete cycle. Reality has been divided into intervals larger than memory itself. The universe does not hide its greatest story. It simply tells it more slowly than any one lifetime can ever follow. And so, the cloud continues its patient expansion through the darkness, not as an isolated monument to a dead star, but as one quiet sentence in a conversation the cosmos has been conducting with itself for more than 13 billion years. Its voice is almost silent. Its consequences echo across galaxies. By now, the scale has become difficult to carry, not because the science has become more complicated, because the mind has quietly reached the limits of the environments it evolved to understand. For millions of years, our ancestors survived by judging distances they could walk, weather they could feel, and dangers they could hear before they saw them. Their success depended upon recognizing patterns measured in meters, hours, and seasons. Natural selection never required them to understand a structure 50 light years across. It never prepared them to imagine an event whose consequences unfold over hundreds of thousands of years. The universe asks us to think with instincts that were designed for forests. That mismatch is one of the great hidden tensions of astronomy. Every time we speak about a supernova remnant, we are attempting to compress realities that exist far beyond human intuition into a language built for ordinary life. Words such as large, old, empty, and far begin to lose their precision. They remain grammatically correct. Emotionally, they fail. This is why astronomy so often produces a peculiar sensation, not confusion, humility, because every honest measurement quietly informs us that our internal picture of reality has always been far too small. Consider the history of our own civilization. The oldest permanent settlements appeared roughly 10,000 years ago. Agriculture transformed scattered communities into cities. Writing preserved memory beyond individual lifetimes. Empires rose, empires collapsed. Religions spread across continents. Mathematics uncovered invisible order. Ships crossed oceans. Factories reshaped landscapes. Electricity illuminated nights. Aircraft conquered the sky. Computers compressed libraries into silicon. Human beings stepped onto another world. To us, this sequence feels immense. Entire academic disciplines exist to study tiny fragments of it. Libraries are filled with the stories of these few thousand years. And yet, against the lifetime of many supernova remnants. The whole of recorded history occupies only a brief interval. If a remnant has been expanding for 20,000 years, then civilization has existed during only part of its journey. If it remains visible for another 50,000 years, every nation alive today will almost certainly have disappeared before its expansion truly ends. Not because civilization is weak, because cosmic clocks do not recognize political ones. History becomes local weather. The cloud continues. This is an uncomfortable comparison because we instinctively measure significance by human duration. A monument surviving for 1,000 years appears eternal. A language lasting 3,000 years seems ancient. A civilization enduring 5,000 years feels almost immortal. The galaxy remains politely indifferent. Its chemistry unfolds across millions of years. Its spiral arms rotate over hundreds of millions. Stars quietly orbit the galactic center for hundreds of millions of years before returning to roughly the same position again. Our entire species has never completed even one galactic year. We often imagine ourselves traveling through the Milky Way. In reality, we have scarcely begun the first sentence of that journey. Even the sun, which feels constant beyond imagination, is moving. It circles the center of the galaxy at roughly 220 kilometers every second. Yet despite that astonishing speed, one complete orbit requires approximately 230 million years. When the dinosaurs first appeared, the sun occupied an entirely different region of the Milky Way. Since then, it has not even completed one full revolution. Every human who has ever lived was born during almost exactly the same tiny segment of that orbit. We have mistaken one frame of an immense film for the entire story. Perspective quietly collapses again. Now return to the supernova cloud. Its expansion, which once appeared unimaginably vast, becomes only one process among countless others unfolding simultaneously. The cloud moves. The star that produced it once orbited the galaxy. The galaxy itself moves relative to neighboring galaxies. Those galaxies drift within the local group. The local group falls toward larger gravitational structures. Nothing remains fixed. The universe has no permanent stage upon which events unfold. The stage itself is always moving. This has profound psychological consequences. Human beings long for reference points, north and south, sea level, the horizon, the rising sun. Stable landmarks reassure us because they simplify reality. Cosmology gradually removes every one of them. There is no universal center, no privileged direction, no cosmic up or down. Even motion becomes relative. The cloud is not expanding into an empty container called space. Space itself participates in the larger evolution of the universe. Reality becomes increasingly difficult to picture because the familiar scaffolding has disappeared. And yet there is another collapse waiting beneath this one, the collapse of importance. It is tempting to assume that intelligence changes the balance, that because we ask questions about the universe, we somehow occupy a unique position within it. In one sense, consciousness is extraordinary. So far, it is the only phenomenon we know capable of reflecting upon cosmic history. But extraordinary does not necessarily mean central. A supernova remnant does not alter its expansion because someone observes it. Radioactive nuclei continue decaying whether anyone measures them or not. Shock waves continue crossing interstellar space through regions that no telescope will ever image. Entire molecular clouds collapse in darkness where no civilization exists to celebrate the birth of new stars. Reality does not wait for witnesses. This idea has accompanied astronomy since the scientific revolution. Each generation has discovered that humanity occupies a smaller position than previously imagined. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The Milky Way is not the center of the universe. Even our observable universe may represent only one accessible region of a larger reality whose full structure remains unknown. The direction of discovery has remained remarkably consistent, not toward greater human importance, toward greater cosmic context. Some find this unsettling, others find it liberating. Both responses arise from the same observation. The universe is astonishingly unconcerned with our presence. And yet, paradoxically, this indifference gives our existence an unusual beauty, because every act of understanding occurs without invitation. The cosmos never asked to be studied. It simply became knowable against overwhelming odds. Matter organized itself into living organisms capable of curiosity. Curiosity became science. Science became a bridge stretching across distances no body could ever travel. Through equations, telescopes, and patient observation, the human mind has begun exploring environments it will never physically enter. We cannot stand inside a supernova cloud, yet we have reconstructed its history. We cannot witness millions of years passing, yet we have learned to infer them from light arriving tonight. Knowledge has become our method of exceeding biology, but even knowledge has limits. No scientist will ever observe one supernova remnant from birth to disappearance. No civilization is likely to survive long enough to do so. Understanding, therefore, remains assembled from fragments. One generation measures expansion. Another improves computer simulations. Another launches better observatories. Each contributes a sentence to a story that no individual will ever finish reading. In this way, science begins to resemble the universe it studies. It, too, becomes cumulative. No single observer contains the whole. The irony is almost poetic. Human beings are temporary creatures, attempting to understand processes that vastly outlive them. We succeed only because understanding itself can be inherited. Ideas survive where observers cannot. Perhaps that is the closest civilization comes to matching cosmic time, not by extending individual lives, but by allowing knowledge to continue traveling after every thinker has become part of history. The expanding cloud does not remember the astronomers who first measured it. Future astronomers may not remember ours. The remnant will continue regardless, yet for a brief interval measured, not in galactic ages, but in human generations. The universe has produced creatures capable of recognizing that the drifting ash of a dead star is also the beginning of countless futures. That recognition is fleeting. The cloud is not. And in the immense silence between those two truths, civilization itself begins to feel less like the destination of cosmic history and more like one passing ripple within it. Once the supernova cloud has grown large enough, something unexpected begins to happen. It stops belonging to the star that created it. At first, this seems impossible. Every fragment within the remnant originated inside a single massive star. Every shockwave began with one collapse. Every expanding filament traces its ancestry back to one catastrophic moment. But galaxies possess a remarkable ability. Given enough time, they erase individuality. A river entering the ocean does not remain a river forever. Its water disperses. Its currents dissolve. Its identity slowly disappears into something vastly larger. A supernova remnant follows the same quiet fate for thousands of years. Astronomers can still identify its expanding shell. Its boundaries remain recognizable. Its chemical composition still carries the unmistakable signature of its origin. Eventually, those boundaries begin to soften. The surrounding interstellar medium seeps inward. The expanding debris spreads outward. Shock fronts weaken. Temperatures gradually decline. The distinction between the remnant and the galaxy becomes increasingly difficult to define. Nothing dramatic announces this transition. No final explosion, no visible collapse, only an almost imperceptible surrender of identity. The cloud ceases to exist, not because it is destroyed, but because it becomes inseparable from everything around it. This is how galaxies breathe, not through lungs, through circulation. The Milky Way is often imagined as a collection of stars floating in empty space. That picture is incomplete. Between those stars lies an extraordinarily thin medium composed of hydrogen, helium, dust, magnetic fields, cosmic rays, and the accumulated debris of countless generations of stellar evolution. Although this interstellar medium appears almost empty by terrestrial standards, it is the environment from which every future generation of stars will eventually emerge. In a sense, it is the galaxy's memory, not memory recorded in words, memory preserved in chemistry. Every supernova enriches this medium. Every stellar wind contributes additional material. Every planetary nebula returns atoms that once spent billions of years locked inside stellar interiors. Nothing remains permanently isolated. Everything returns. Imagine an ancient forest. Leaves fall, branches decay, dead trees collapse, fungi slowly dismantle wood into soil. Nutrients disappear beneath the ground. Years later, entirely new trees rise using those same atoms. No individual leaf survives. The forest does. A galaxy behaves in much the same way. Stars are its temporary trees. Supernovae are not accidents interrupting the forest. They are part of the forest's metabolism. This idea becomes clearer when we consider spiral galaxies like our own. The elegant spiral arms visible in photographs are often mistaken for permanent structures. Like the blades of a pinwheel, they are not. They resemble traffic patterns more than physical objects. Individual stars continuously move through the spiral arms. Gas enters, gas leaves, clouds collapse, new stars ignite, old stars drift away. The arm itself persists because the overall pattern persists, even though almost none of its individual components remain the same. The galaxy is less a sculpture than a flow. Within these spiral arms, molecular clouds gather. They are compressed by gravitational disturbances moving through the galactic disk. Their density increases. New clusters of stars begin to form. Massive young stars illuminate, surrounding gas with brilliant ultraviolet radiation. For a few million years, the region becomes one of the brightest nurseries in the galaxy. Then the most massive of those newborn stars die. Fresh supernovae erupt. Their expanding remnants reshape the surrounding clouds. The cycle begins again. Birth prepares death. Death prepares birth. Neither stage exists independently. When viewed across millions of years, the distinction between them almost disappears. This circulation extends far beyond visible matter. Cosmic rays accelerated by supernova remnants travel enormous distances through the galaxy. Magnetic fields carry their influence into regions that may never directly encounter the expanding shell itself. Radiation alters chemistry. Inside cold molecular clouds, tiny grains of dust accumulate icy coatings where complex molecules begin forming. Simple carbon compounds gradually become more elaborate. Water, methanol, ammonia, organic molecules, not life, but ingredients. The galaxy quietly experiments with chemistry long before biology ever appears. A supernova, therefore contributes far more than heavy elements. It changes environments. It redistributes energy. It influences magnetic structures. It compresses clouds. It modifies chemistry. Its consequences spread far beyond the visible edge of the remnant. The cloud has become a participant in something larger than itself. Perhaps this is why astronomers increasingly describe galaxies as ecosystems, not because they are alive, because they contain countless interacting processes that continuously regulate one another. Energy flows, matter circulates, structures emerge, structures dissolve, feedback shapes future evolution. Nothing exists in complete isolation. A single supernova can trigger star formation in one region while suppressing it in another. Intense radiation may destroy fragile molecules nearby, even as distant shock waves encourage new clouds to collapse. The same event creates opposing outcomes depending upon location. Nature rarely chooses only one consequence. This complexity makes prediction extraordinarily difficult. Computer simulations attempting to reproduce galactic evolution require astonishing computational power. Researchers must model gravity, hydrodynamics, magnetic fields, radiation, turbulence, chemistry, stellar evolution, and dark matter simultaneously. Even then, uncertainties remain. Not because the laws of physics are unknown, because billions of interacting processes produce behavior too intricate for perfect foresight. The galaxy is lawful. It is not simple, and this complexity hides another profound implication. Every star you see tonight occupies only a temporary address. The Sun itself was born from one region of the Milky Way. Over hundreds of millions of years, it has continued its orbit around the galactic center, passing through changing environments as spiral arms slowly moved relative to its path. Long after humanity is gone, the Sun, if it still exists, will continue traveling. Eventually, it will leave the neighborhood familiar to us today. Different stars will surround it. Different molecular clouds will drift nearby. Different supernova remnants may expand across the darkness. Even stellar neighborhoods are temporary. Nothing in the galaxy remains permanently local. This quiet migration changes the meaning of home. We often imagine the solar system as anchored to a fixed position within the cosmos. In reality, it is more like a traveler crossing an immense continent whose landscapes change almost too slowly to notice. Every orbit around the galactic center introduces new surroundings. Every 100 million years presents an unfamiliar sky. If intelligent observers exist elsewhere in the Milky Way, separated by tens of thousands of light years, they are not merely distant in space. They may also occupy entirely different chapters of the galaxy's ecological history. One civilization could emerge within a region freshly enriched by generations of supernovae. Another might arise in an older, quieter environment where star formation has slowed dramatically. Their galaxies would be the same. Their galactic experiences would not. The Milky Way is not one place. It is billions of places connected by time. The supernova cloud now appears differently, no longer as the isolated remains of a dead star, no longer even as the birthplace of future stars. It has become a moving participant within a living circulation of matter, energy, and history that spans the entire galaxy. Its identity gradually dissolves into something much greater, and perhaps that is the quiet destiny of everything. Atoms lose themselves within clouds. Clouds lose themselves within galaxies. Galaxies lose themselves within larger cosmic structures. Nothing is truly discarded. Nothing remains entirely separate. The universe does not preserve individuality forever. Given enough time, it gently folds every separate story back into a larger one. The cloud, which once seemed like an ending, has become a current within an ocean whose tides have been flowing for billions of years. Its explosion was only the moment it entered that current. Its true journey is the one that follows. There is a silence so complete that the human mind instinctively refuses to believe it exists. Not because silence itself is unfamiliar, but because every silence we have ever experienced has always contained the possibility of interruption. A forest grows quiet before dawn. Somewhere, a bird will eventually sing. A winter field lies still beneath falling snow. Sooner or later, the wind will return. Even the deepest ocean, far below the reach of sunlight, remains filled with slow currents. Distant whale calls, shifting rock, and the endless whisper of moving water. On Earth, silence is temporary. It waits for sound. The silence between the stars waits for nothing. A supernova remnant expands into that silence. Its shock waves carry extraordinary energy. Its particles race outward at thousands of kilometers each second. Magnetic fields twist through its plasma. Radioactive nuclei quietly decay. Electrons spiral around invisible lines of force. Everything is happening. Nothing can be heard. This absence of sound is more than an interesting scientific detail. It changes the emotional character of the universe itself. Human beings instinctively associate noise with life. Cities hum, rivers rush, animals call to one another, machines vibrate, even our own bodies constantly produce sound, the rhythm of a heartbeat, the movement of breath, the circulation of blood. Silence often makes us uncomfortable because it suggests absence. The galaxy extends that absence almost beyond comprehension. Imagine standing beside the expanding shell of a supernova remnant, not watching it through a telescope. Standing there, the shock front might be moving hundreds or even thousands of kilometers every second. The surrounding plasma might glow fiercely in X-rays. Cosmic rays might be streaming through the region with astonishing energies. Yet your ears would receive nothing. Not because the event lacks violence, because violence itself has been separated from sound. The explosion has become mute. Our brains are poorly equipped to imagine this. Cinema has trained us to expect roaring stars, booming explosions, and deep mechanical vibrations accompanying cosmic events. Reality offers something stranger. The most energetic phenomena in the visible universe often unfold in complete acoustic emptiness. The silence is not dramatic. It is indifferent, and it extends far beyond the cloud itself. The nearest star beyond the sun, Proxima Centauri, lies more than 4 light-years away. That distance is usually introduced as an impressive measurement. Its emotional meaning is often overlooked. If the sun vanished this very moment, a purely hypothetical event forbidden by known physics, Earth would continue orbiting normally for just over 8 minutes before the last sunlight arrived and gravity's final influence reached us. Scale that outward. If an identical event occurred at Proxima Centauri, more than 4 years would pass before we could know. For over 4 years, reality would have already changed while our knowledge remained trapped in the past. Distance becomes delayed awareness. The galaxy is full of such delays. Most stars never come close to one another, even within the crowded regions of the Milky Way. The average separation between neighboring stars remains immense. Entire planetary systems travel through darkness with no nearby companions, except faint points of light separated by trillions upon trillions of kilometers. If intelligent observers exist around those stars, they almost certainly spend their nights beneath skies that look isolated, not empty, separated. The difference matters. Isolation is not the absence of everything. It is the overwhelming presence of distance. A supernova remnant illustrates this perfectly. Its expanding shell may span dozens of light years. Inside that enormous volume, particles remain astonishingly sparse. Outside it, the next major structure may lie even farther away from the perspective of any single atom drifting through the remnant. Encounters are extraordinarily rare. Most of existence consists of uninterrupted travel through darkness. This is the normal condition of matter, not gathering, not colliding, drifting. The same principle shapes galaxies themselves. When we admire photographs of the Milky Way from outside, imagined through simulations or inferred from observations, we see luminous spiral arms wrapped around a brilliant central bulge. The image feels crowded, rich, full, but photographs compress three-dimensional space into two dimensions. Perspective quietly performs another deception. If every star in the galaxy were reduced to the size of a grain of sand while preserving their relative distances, each grain would still lie astonishingly far from its nearest neighbor. The spiral pattern would remain visible. Walking from one grain to the next would become an extraordinary journey. The beauty survives because emptiness supports it. Without immense separation, galaxies could not exist in their familiar form. The stars would continually disrupt one another. Planetary systems would struggle to remain stable. Darkness, rather than being an unfortunate absence, becomes the condition that allows order to persist. The void is not the opposite of structure. It protects structure. This reversal appears again and again throughout astrophysics. The things we instinctively dismiss as empty often prove essential. Vacuum allows light to travel enormous distances without being scattered away. Sparse interstellar gas permits stars to orbit peacefully for billions of years. The enormous gaps between galaxies preserve their identities across cosmic time. Emptiness is not merely what remains after matter has been removed. It is one of the defining features of reality itself. Yet this same emptiness creates an uncomfortable emotional consequence. Loneliness, not human loneliness, cosmic loneliness. Every civilization that has ever existed on Earth has shared one planet beneath one atmosphere. No matter how distant two cultures became, they remained connected by the same oceans, the same moon, and the same sun. The galaxy offers no such intimacy. If intelligence exists elsewhere, and we do not yet know whether it does, then almost every civilization would be born into extraordinary isolation, separated not by oceans, but by light years, not by months of travel, but by intervals that light itself requires years, centuries, or millennia to cross. Communication becomes history. Conversation becomes archaeology. A greeting sent today might not arrive until long after the civilization that transmitted it has transformed beyond recognition. Replies may return to worlds that no longer resemble the ones that first listened. The universe does not merely separate places, it separates moments. The supernova cloud drifts through this isolation without complaint. It neither seeks companionship nor avoids it. Its particles expand because momentum demands expansion. Its magnetic fields evolve because physics permits evolution. Its radiation spreads equally in every direction, unconcerned whether any observer waits to receive it. This indifference can feel unsettling when viewed from a human perspective. We naturally search for reciprocity. We speak because someone may answer. We create because someone may remember. The cloud does neither. It simply continues. Perhaps that is why images of supernova remnants evoke such complicated emotions. They are undeniably beautiful. Their colors appear almost delicate. Their forms resemble lace suspended against darkness. Yet every photograph also captures profound separation. The glowing filaments occupy only tiny fractions of the space surrounding them. The rest is almost entirely empty. The cloud itself, magnificent as it appears, is largely a portrait of absence. And that absence extends outward, beyond the remnant, beyond the neighboring stars, beyond the spiral arms, beyond the visible edge of the galaxy. The farther astronomy has looked, the more persistent the pattern has become. Matter gathers briefly, then vast darkness resumes. Light appears, then silence continues. Worlds form, then unimaginable distances separate them again. The universe is not built from islands connected by oceans. It is built from rare islands surrounded by a sea so immense that the islands themselves almost disappear. The supernova remnant is one such island, brilliant for a while, transformative for a while, then gradually dissolving back into the larger silence from which the next generation of stars will one day emerge. Its greatest lesson may not be the violence of its birth. It may be the extraordinary emptiness into which it spends the rest of its existence expanding, because in that emptiness, the true scale of reality finally becomes impossible to ignore. After enough distance, the science begins to feel strangely personal, not because the universe has become smaller, because the boundary between the observer and the observed has quietly disappeared. For most of this journey, the supernova cloud has remained comfortably distant. It has existed as an astronomical object, measured in light years, photographed by telescopes, analyzed through spectroscopy, and reconstructed by equations. It has belonged to the heavens, but that distinction has always been incomplete. The cloud is not merely something you are looking at. It is something you are made from. This statement has become familiar enough to risk losing its meaning. We are made of stardust. It appears in documentaries, classrooms, books, and speeches. It has become almost poetic through repetition. Yet beneath the poetry lies an extraordinarily precise scientific claim. The hydrogen in your body is ancient. It was created during the first few minutes after the Big Bang, when the young universe cooled enough for the simplest atomic nuclei to survive. It has traveled through more than 13 billion years of cosmic history. Everything else followed a different path. The carbon in your cells, the oxygen entering your lungs, the calcium supporting your skeleton, the iron moving through your blood, the phosphorus storing chemical energy inside every living cell. These atoms were manufactured later, not together, not in one place, not even during the same era of galactic history. Each possesses its own biography. Long before Earth existed, those atoms were scattered across the Milky Way in entirely different forms. Some spent millions of years buried inside the cores of ancient stars. Others drifted through molecular clouds before becoming incorporated into another stellar generation. Some were thrown into darkness by supernova explosions that occurred before our sun had even begun to form. Their journeys cross at immense distances and unimaginable spans of time. Only by remarkable coincidence, or perhaps by the inevitable consequences of gravity and chemistry, did they eventually meet again inside one small rocky planet orbiting an ordinary yellow star. Even then, their journey was not over. The early Earth was hostile beyond modern imagination. Its surface was repeatedly struck by asteroids. Volcanoes reshaped continents that had not yet fully formed. Atmospheres changed. Oceans appeared. Chemistry slowly explored possibilities across hundreds of millions of years. Most combinations failed. Some persisted. Eventually, matter crossed an invisible threshold. It began organizing itself, not into stars, into life. This transition remains one of science's deepest mysteries. Researchers continue investigating how non-living chemistry gradually became biology. The details remain uncertain, yet whatever the precise pathway, one fact is unavoidable. The atoms themselves remained ordinary. Carbon did not become alive. Oxygen did not become conscious. Iron did not acquire intention. Only their arrangement changed. The same elements that once drifted silently through a supernova remnant eventually participated in something capable of memory, curiosity, and reflection. The difference lay not in the material, but in the pattern. This idea carries an unexpected emotional consequence. Human beings often search for uniqueness in composition. We imagine that life must contain some special substance absent from the rest of the universe. Modern astronomy quietly dissolves that expectation. The chemistry inside your body is astonishingly familiar. The universe has been producing these elements for billions of years. Nothing in your bloodstream would surprise a dying star. Nothing in your bones would seem exotic to a supernova remnant. The extraordinary aspect is not what you are made of. It is how those ingredients have been organized. Imagine dismantling a library. The paper remains, the ink remains, the shelves remain. Every physical component still exists. Yet the stories disappear because their arrangement has been lost. Biology resembles literature more than architecture. Its meaning emerges from relationships rather than ingredients. The universe spent billions of years manufacturing the alphabet. Life slowly learned how to write. This perspective changes the way we think about mortality. On Earth, death often feels like disappearance. An individual life ends. Memories fade. Voices fall silent. The body gradually returns its material to the surrounding world from the viewpoint of chemistry. However, almost nothing has been lost. Atoms simply continue traveling. The carbon that once helped form a human brain may eventually become part of a tree. The oxygen exchanged during your final breath may circulate through oceans before entering another organism centuries later. The calcium within your skeleton may one day dissolve into rivers, settle into marine sediments, or become locked inside future mountains. Matter rarely rests. It only changes companions. The supernova remnant demonstrates this principle across a far greater scale. Its expanding cloud appears temporary because the visible structure eventually fades. The atoms themselves continue. They become part of molecular clouds, stars, planets, atmospheres, perhaps somewhere, another living mind. The cloud vanishes, its material does not. This is both comforting and unsettling. Comforting because nothing is truly discarded. Unsettling because permanence belongs only to matter, not to identity. The atoms that currently compose your body have belonged to countless previous structures. They will belong to countless future ones. None of those structures will be you. Identity, like a wave crossing the sea, exists for a time without ever possessing the water through which it moves. The wave disappears. The ocean remains. Astronomy repeatedly returns us to this distinction. Stars are temporary. Galaxies evolve. Even the visible universe changes with time. Patterns emerge. Patterns dissolve. The underlying matter and energy continue participating in new arrangements. Nothing lasts forever. Almost nothing is truly lost. Perhaps this is why studying supernova remnants evokes emotions that extend beyond science. They reveal that permanence has never been the operating principle of the cosmos. Continuity has. The universe preserves processes more faithfully than objects. Hydrogen becomes stars. Stars become heavier elements. Heavy elements become planets. Planets become chemistry. Chemistry becomes biology. Biology becomes consciousness. Consciousness begins asking where the hydrogen came from. The cycle briefly closes, then it opens again. This perspective also reshapes the meaning of ancestry. Human families usually trace their histories through parents and grandparents. Civilizations look toward founders. Cultures preserve myths explaining origins. The universe offers a genealogy extending incomparably farther. Your oldest ancestor is not a person, it is a sequence of physical events. The first minutes after the Big Bang, the birth of early stars, the explosions that enriched the galaxy, the collapse of molecular clouds, the formation of the solar system, the long geological evolution of Earth, the slow emergence of life. Every generation inherits not only DNA, but cosmic history. The inheritance is written into every atom, not as memory, as composition. This quiet realization changes the emotional relationship between humanity and the night sky. The stars cease to be distant decorations. They become older relatives whose lives ended long before ours began. The glowing remnants scattered across the Milky Way are not merely astronomical curiosities. They are chapters from a family history extending across billions of years. Most of that history unfolded without observers. Most of it remains inaccessible. Yet enough survives in the chemistry of our own bodies that the story can be partially reconstructed. In an extraordinary twist, the universe has produced creatures capable of discovering that they carry fragments of extinct stars within themselves, not because the cosmos intended recognition, because the evidence remained. The atoms never forgot, they simply continued existing until something evolved that could finally read the record they had been preserving all along. Perhaps that is the quiet miracle hidden inside every supernova cloud. Not that it creates beauty, not even that it creates future worlds, but that, after billions of years of wandering through darkness, a tiny fraction of its atoms may eventually assemble into beings capable of looking back toward the expanding ash from which they came and recognizing themselves. There is one final illusion that still remains. It is the quiet belief that the universe is moving toward completion. Human beings naturally think in destinations. A child grows into an adult. A building is eventually finished. A journey ends when the traveler arrives. Stories resolve. History advances. Even death is often imagined as a final chapter, beyond which no further change occurs. The universe almost never behaves this way. A supernova cloud reveals why. Throughout this journey, it has been tempting to imagine the remnant as a bridge between two states. A star dies. A cloud expands. New stars eventually form. The cycle repeats. The sequence feels satisfying because it resembles the structure of a story. But stories belong to minds. Physics belongs to processes. The cloud is not traveling toward a final purpose. It is participating in a chain that possesses no known beginning beyond the earliest moments of the observable universe, and no known ending within any timescale that human imagination can comfortably hold. This is where cosmic scale becomes almost psychologically unbearable, because the further astronomy looks into the future, the less familiar the future becomes. For now, the Milky Way remains rich with cold hydrogen. Star formation continues. Massive stars are still being born. Supernovae still enrich the galaxy with heavy elements. The cycle feels almost eternal, but galaxies are not inexhaustible. Every new generation of stars consumes a little more of the available gas. Some material becomes locked inside long-lived, low-mass stars that may burn quietly for trillions of years. Some falls into stellar remnants. Some escapes the galactic disk altogether. The Great Circulation continues. Its reservoirs slowly diminish. This is not a crisis. It is simply time expressing itself. Millions of years pass almost unnoticed. Hundreds of millions reshape spiral arms. Billions alter galaxies. Trillions transform the universe itself. The future revealed by modern cosmology is not dramatic. It is gradual. The Milky Way will continue producing stars for billions of years. Eventually, star formation will slow. The brilliant blue giants that now illuminate stellar nurseries will become increasingly rare. Galactic skies will change. Future observers, if any remain, may inherit a quieter universe than ours. The great stellar foundries will not suddenly stop. They will slowly become less frequent. The universe does not often close doors. It leaves them gently swinging until almost no motion remains. The supernova cloud therefore belongs to a particular era, not the beginning, not the end. Any age of active creation, an age when galaxies still possess enough fuel to manufacture new suns. We happen to exist during one of the richest periods in cosmic history. This observation is both comforting and unsettling. Comforting because the universe surrounding us remains astonishingly productive. Unsettling because productivity itself is temporary. Nothing in cosmology suggests that today's conditions will continue forever. The future grows quieter and quieter. Imagine visiting an immense city at midday. The streets are crowded. Construction cranes fill the skyline. New buildings rise while older ones are carefully dismantled. Traffic flows continuously. The city feels alive. Now imagine returning after every inhabitant has slowly departed over millions of years. The buildings remain for a while. Weather gradually erodes them. Roads crack. Lights go dark. Eventually, only scattered ruins remain, not because disaster struck, because activity simply faded. Cosmologists sometimes speak of a similar future, not the sudden destruction of galaxies, the gradual exhaustion of opportunities. The great stellar factories become increasingly quiet. Supernovae become less common. Heavy element production slows. The universe continues existing. It simply changes its rhythm. Them ability transforms the meaning of every supernova remnant we observe today. They are not merely records of stellar death. They are evidence that we inhabit an active universe, one still capable of astonishing transformation, one still manufacturing the ingredients from which future worlds may emerge, one still writing new chapters, but no chapter continues forever. Even the galaxies themselves will not remain isolated. Astronomers have measured the motion of the nearby Andromeda galaxy with extraordinary precision. It is approaching the Milky Way, not rapidly by human standards, inevitably by cosmic ones, roughly 4 to 5 billion years from now. The two galaxies will begin a prolonged gravitational encounter, contrary to popular imagination. Most individual stars will almost certainly never collide. Space is far too empty. Instead, gravity will reshape entire galactic structures. Spiral arms will stretch. Gas clouds will compress. New waves of star formation may ignite. Fresh generations of massive stars will live brief, brilliant lives before exploding as supernova. Even galaxies recycle themselves. The scale simply becomes larger. What once seemed like a complete system reveals itself as one stage inside another, exactly as the supernova cloud did. The pattern repeats again. Every apparent ending opens into a broader process. Every broader process eventually becomes part of something larger still. The human mind continually expects the final layer. Astronomy has not yet found one. Even our observable universe possesses limits created by the finite speed of light. Beyond that horizon may lie regions forever inaccessible, not because they do not exist, because light has not had sufficient time to bridge the expanding distance. Reality may extend unimaginably farther, or it may possess structures unlike anything current cosmology anticipates. Science remains honest here. The uncertainty is genuine, yet even within the observable universe alone, The scale already overwhelms intuition. Hundreds of billions of galaxies, each containing hundreds of billions of stars, each star participating in histories spanning millions or billions of years, each generation inheriting matter from previous generations. The supernova cloud now appears almost modest. What once seemed unimaginably vast has quietly become one local event inside a universe whose full architecture remains only partially understood. Perhaps this is the most unsettling implication of all. Every expansion of knowledge has reduced the apparent centrality of previous understanding. The Earth became one planet. The Sun became one star. The Milky Way became one galaxy. The observable universe itself may represent only one accessible region of a still larger reality. The direction has remained remarkably consistent, not toward simplicity, toward greater context. The cloud reflects this pattern perfectly. Its visible beauty conceals invisible machinery. Its machinery belongs to galactic ecology. Galactic ecology belongs to cosmic evolution. Cosmic evolution unfolds within a universe, still revealing new layers whenever observation becomes more precise. There is no evidence that the unfolding has reached its conclusion, only evidence that every conclusion so far has become another beginning. This leaves humanity in an unusual position. We are neither spectators standing outside the process, nor permanent participants within it. We are one temporary arrangement of matter observing another. The atoms inside our bodies have already survived extinct stars. They may one day survive extinct planets, long after Earth is gone. Some fraction of its material will continue traveling through whatever future the cosmos still contains. Identity will disappear. Matter will continue. Process will continue. The cloud understands this without consciousness. Its expanding shell never asks where it is going. It simply obeys momentum. The galaxy never wonders why stars form. Gravity continues its patient work. The universe never pauses to consider its own future. It unfolds. Perhaps consciousness is the only phenomenon that finds this unsettling. The cosmos itself appears perfectly content with endless transformation. The final revelation, then, is not that supernova clouds are terrifying because they are violent. They are terrifying because they reveal that permanence has never been the natural language of reality. Everything we call stable is merely changing more slowly than we are. The cloud expands, the galaxy evolves, the universe ages, and the distinction between beginning and ending grows fainter with every increase in scale. What remains is not a destination, only an endless succession of transformations, each quietly giving rise to the next, while the darkness between them patiently waits without ever truly being empty. After enough time, even astonishment becomes quiet, not because the universe has become less extraordinary, because the mind has slowly stopped resisting its scale. At the beginning of this journey, the supernova cloud seemed like an event. Then it became an environment. Then a participant in the life of a galaxy. Then one expression of processes stretching across billions of years. Now, standing at the edge of everything we have uncovered, it no longer asks to be understood in isolation. It asks only to be seen for what it has always been, a moment inside a much longer story. There is something unexpectedly peaceful about that realization. Human beings spend much of their lives searching for permanence. We preserve photographs because faces change. We build monuments because memories fade. We write books because voices fall silent. Every act of preservation quietly admits the same truth. Nothing familiar remains exactly as it is. Astronomy does not contradict this instinct. It enlarges it. The same impermanence that touches every human life also shapes stars. galaxies. And the great clouds drifting between them, the difference is only one of scale. A flower blooms for days. A civilization flourishes for centuries. A star burns for billions of years. A galaxy evolves across intervals almost impossible to imagine. Each seems permanent when viewed from within its own timescale. Each eventually changes. Perhaps permanence has always been a matter of perspective rather than duration. The supernova remnant demonstrates this with remarkable elegance. To an observer living for a single day, nothing inside the cloud appears to move. To an observer capable of waiting 10,000 years, the expansion becomes unmistakable. To an observer existing for a billion years, even the remnant itself would seem brief, a passing phase before its material disappeared into larger galactic currents. Every lifespan creates its own illusion of stability. Reality remains patient beneath them all. There is another quiet thought hidden here. The cloud has no memory. It does not remember the star whose interior it once occupied. It does not remember the collapse that accelerated its particles outward. It carries evidence of those events. But evidence is not remembrance. The distinction matters. A fossil preserves the shape of an extinct creature. The fossil itself remembers nothing. Tree rings preserve years of changing climate. The tree does not recall each winter. The atoms drifting through a supernova remnant preserve an astonishing history of stellar evolution. They possess no awareness of it. Memory belongs to living minds. History belongs to matter. For a brief interval, those two become connected. Astronomers read the chemistry of expanding gas. Physicists decode the energy carried by radiation. Mathematics reconstructs explosions that occurred before many civilizations were born. Knowledge emerges because consciousness learns to interpret patterns that matter has quietly preserved. The universe never wrote its history as a story. It wrote it as structure. Perhaps this is why the night sky feels different after understanding even a small part of it. The stars lose none of their beauty. If anything, they become more beautiful, but their beauty changes character. It no longer comes from mystery alone. It comes from continuity. Every point of light belongs to processes extending far beyond itself. Every dark region conceals possibilities invisible to ordinary sight. Every faint nebula drifting through the Milky Way represents either the memory of previous stars or the beginning of future ones. Nothing stands entirely alone, not even silence. Even silence has a history. The darkness between stars was shaped by the stars surrounding it. The emptiness inside a remnant was created by the outward rush of matter. The calm visible in a telescope image exists only because human lives are too short to witness the motion hidden within it. Stillness, once again, proves to be another form of movement observed too briefly. There is comfort in accepting this, not because the universe becomes more welcoming. It does not. The distances remain overwhelming. The silence remains immense. The future remains indifferent to every civilization now alive. None of those realities have changed. Only our relationship with them has. We stop expecting the cosmos to resemble human experience. We allow it to remain itself. And in doing so, something curious happens. The fear softens, not because the universe has become smaller, because we have stopped asking it to fit inside familiar ideas. The supernova cloud no longer appears monstrous, nor does it appear gentle. It simply exists, a magnificent consequence of gravity, nuclear physics, time, and emptiness acting together with extraordinary patience. Its expansion requires no audience. Its beauty requires no admirer. Its future requires no prediction. It will continue whether or not anyone remains to observe it. There is a quiet dignity in that independence. Long after the last observatory has fallen silent, long after every spacecraft launched from Earth has ceased transmitting. Long after the final language spoken by humanity has vanished from memory, the atoms released by ancient supernovae will still be traveling. Some will become part of stars that have not yet ignited. Some will remain suspended between galaxies. Some may drift through darkness so profound that they never again approach another world. None will know the difference. Perhaps, in the end, this is what the expanding cloud has been teaching all along. Reality is under no obligation to preserve the forms we temporarily recognize. It preserves only the possibility of new ones. The universe does not hold tightly. It lets go. Again and again, stars let go of their interiors. Galaxies let go of their gas. Planets let go of their atmospheres. Living creatures let go of the atoms they briefly arranged into thought. Nothing is kept forever. Everything is returned. The cloud drifting silently through interstellar darkness is neither a monument to loss nor a promise of renewal. It is simply the place where one arrangement ended and countless unseen possibilities quietly began. And perhaps that is enough. Perhaps it has always been enough, because the universe has never asked for permanence, only participation. For a little while, every star participates. For a little while, every world participates. For a little while, every living mind participates. Then each becomes part of the larger circulation once again. The cloud does not mourn that passage. It continues, expanding through the darkness with the same quiet patience that has always guided the stars. Eventually, every photograph fades into darkness, not because the cloud has disappeared, because the light becomes too faint. The expanding shell grows larger. Its edges become thinner. Its energy disperses across an ever-increasing volume of space until the remnant gradually loses the sharp identity that once made it visible. Astronomers stop calling it a supernova remnant. The galaxy quietly accepts it back. Nothing announces the moment. There is no final flash, no closing movement, only an almost invisible transition from something recognizable into something ordinary. Perhaps that has always been the true nature of the universe. Its greatest transformations rarely occur all at once. They unfold so patiently that only time itself notices. Somewhere tonight, another massive star is approaching the end of its life. No observer can say precisely which one. Its light appears calm. Its surface continues, shining across the darkness, exactly as it has for thousands, perhaps millions of years, deep within its core. However, gravity is patiently continuing a conversation that began long before our species existed. One day, balance will fail, the star will collapse, a new cloud will begin its slow expansion. New heavy elements will enter the galaxy. New molecular clouds may eventually inherit them. New stars may ignite. Perhaps new worlds will cool beneath unfamiliar skies, perhaps somewhere. After another immeasurable sequence of transformations, another curious mind will look upward and wonder where everything began. It will discover, as we have, that there was never a single beginning, only earlier chapters, and behind those chapters, still earlier ones. The expanding ash of extinct stars will continue drifting through a universe that neither celebrates nor regrets their passing. The darkness between them will remain immense. The silence will remain complete. The distances will continue exceeding imagination. Yet within that silence, the slow circulation of matter will never truly stop. Atoms will continue changing companions. Clouds will become stars. Stars will become clouds again. Galaxies will patiently reshape themselves, while no witness survives long enough to watch the entire performance. The universe does not hurry. It has no reason to. For creatures whose lives are measured in decades, this perspective can feel unsettling, but perhaps there is another way to understand it. The cosmos has never promised permanence, only continuity. The atoms that briefly became a dying star were never lost. The atoms that briefly became a supernova cloud were never lost. The atoms that briefly became oceans, forests, mountains, and living minds will not be lost either. Only the patterns change. Only the names change. Only the stories pause before new ones quietly emerge. And so the cloud continues, not toward a destination, not toward an ending, only outward, through a darkness vast enough to hold every past and every future at once. Long after every human memory has faded, its journey will still be unfolding patiently, silently, almost imperceptibly within a universe whose greatest truth was never violence, nor emptiness, nor even scale. It was transformation, and transformation, unlike any star, never truly dies.